Okay, let's talk about a priority queue. Priority queue is a data structure that organizes a collection of items so that we can delete and take the extreme value. There are several approaches for implementing priority queue. We can use an ordered array, and every time we know the extreme value is at the last index. So delete maximum cost 1. However, in order to insert a new item, we need to move the item's rightward in order to empty a new slot. The cost for insertion, in average, is proportional to n. Another approach is to use an unordered set. Insertion cost is 1, but delete maximum need to read through each item in the set. The cost is proportional to n. We want an algorithm with reasonable insertion cost and delete maximum cost. Natural tree can inspire us. It has branches to put more material on. Gravity also put priority at the root. So let's have two definitions to extract the successful factor of the tree. Binary tree. A tree whose elements have at most 2 children is called a binary tree. We don't want many trees. We don't want many nodes. 2 nodes is very simple and also get the essence of the tree. Heap order. The value of each node is greater than or equal to the value of its parent. Heap order, we can also say the value of each node is smaller than or equal to the value of its parent. So it depends on its maximum heap or minimum heap. Now we have the heap ordered binary tree. It is already a priority queue because the extreme value is at the root. If we want to add a new item, we add it as a tip. If the heap order is violated, we can fix it by exchanging the parent and the child. In the worst scenario, we have to swim a new node from the tip to the root. The total comparison is no bigger than the height of the tree. So if we have a meaning item, the ordered array need to do about half meaning move and comparison in order to insert it. But for heap order binary tree, we just have to do 20 comparison and move. For delete maximum, we get the value of the root. Then we delete it by change the root with the item in the tip. Now the heap order is violated. We can exchange the parent and child until the heap order is restored. And the cost of the swamp and comparison is no bigger than the height of the tree, which is logN. So heap ordered binary tree have logN cost for both insertion and delete maximum. Now we have the idea. Let's write a program. In order to write a program, we can use an array to represent a heap order binary tree. The index is a node. We get a parent node by dividing 2. We get the left child by multiply 2. The right child is just 1 index right. So for index 3, the parent node is at 1. For computers, 3/2, we take the floor, which is 1. So both 2 and 3 have the common parent 1. And the 2 child node is at 6 and 7 accordingly. By the way, we don't use index 0, just for convenience. 0 multiply 2, divide 2, just go nowhere. So here is a program. First, this is a backup array, and we also need a size. At beginning it's 0, empty. Now let's write the constructor. We want the size to be bigger than the maximum size because we want to use the first item. Let's write a helper function too. Now have this helper function. Our next step is write the swim. So after we added a new item, we want to swim it to the top. Where it is not at the root, and the heap order is violated. Here we are dealing with a maximum priority queue. If the heap order is violated, we exchange it, and for each loop we want to decrease the index. Now we have the swim. Insert is just one step away. We increase the size, and we put a new item there. Now the heap order is violated. We just have to fix it. That's for insertion. Now let's write a program function for sync. We just remove the root. We put a new item there. We need to sync it down. Pride 2 below or equal n. Let's get the index of the left child. In the case the right child is bigger, we want to take the index of the right child. Then we just have to exchange for each iteration. We increase the index. Now we have the sync. Okay, next let's write the deleteMax. We know the maximum value at index 1. We just have to return it. Simple. However, we need to fix the ruined tree. We fix it easily. We just exchange 1 with minus minus n. Oh, n minus minus. we decrease the size, and we just sync one, and that's the delete maximum. Now let's write a program to verify our implementation. Okay, we haven't created PriorityQueue yet. Okay, so let's randomly insert. Size. Oh, we have an implement size. Okay. Public and okay. We randomly insert some item, but print out from the biggest to the smallest in decreasing order, so our implementation is correct. The cost is logN for insertion and logN for delete maximum. This is a priority queue.